Hello and welcome to the overview of our electric supercharger project at Clemson University. Turbochargers and superchargers are forced induction systems that increase the power of a vehicle by compressing and pushing more air into an internal combustion engine. And turbochargers work off of exhaust gases, which would mean that they require a custom exhaust system, while superchargers utilize a pulley system that's connected to the vehicle's engine's crankshaft. And both of those systems have quite a few disadvantages. In the case of turbochargers, there is delay in when boost can be provided, and superchargers put additional load on the engine. And the biggest disadvantage is that neither of those systems provide direct control over how much and when boost is being built. So the goal of our project was to design a standalone forced induction system that eliminated the need for extensive modifications, such as custom exhaust or a pulley system. We also aim to make the system more controllable by reading vehicle data through the OBD2 port. And we also use the pressure sensor for feedback. And to compete with other products on the market, we set a goal of achieving at least 5 psi of boost.
So this is the block diagram of our project. The ECU sends data to the Raspberry Pi, which then sends data to the user interface, which allows it to display on the screen. It also sends a PWM signal to the motor controller, which in turn controls the motor, which spins up the supercharger to produce boost. The motor controller has a battery management system along with its batteries.
So for the software design of our supercharger, the motor control, we'll be using CAN data, which is a controller area network through OBD2 port in the car onboard diagnosis port. We'll be reading various values to use for the project. We'll especially be focusing on throttle position to determine how much boost we'll be using depending on the profiles the user select. As you can see in the chart, we'll be reading in throttle positions and determining if it's within the range the boost would be produced. We'll also be using pressure sensor data to make sure that we're getting enough pressure PSI for the motor. Also, we'll be using PID controls to ensure the pressure is achieved at the right throttle. Now we'll talk about user interface. We have defined 3 different profiles for a user to choose from: Eco, Sport, and Racing. Once the user has selected a profile, it can select the Start button, and it would go into the profile. And once in the profile, the program will monitor throttle position, RPM, and many more variables depending on the one that you select. According to those, the boost would be produced. For the user interface, the GUI part of it, as you can see, we have user selecting max PSI for the motor and then also selecting a profile. We also have T0 and T100, which is used for the throttle position depending on the car, because different cars have different throttle positions. We also have gauge, which shows the speed, throttle position, RPMs, and the pressure.
So methodology for the OBD2 reading. Data from the ECU of the car is transmitted over a port known as the OBD2 port. This is a standardized port that was standardized and passed in 1994, which was required on all cars produced after 1996. For this, we have an ELM 327 module, which allows us to take data from the OBD2 port, which is over a CAN bus line, a standardized CAN bus line. As you can see, the SAE J1850 bus and also the ISO 15765-4 data bus. These two are 2 SAE, Society of Automotive Engineers standards that are required by law for all new cars post 1996 to have. And then, of course, the other one is not post 2008. The ISO 15765-4 is a post 2008 standard. The ELM 327 uses a chip which allows us to take this CAN data and send it over a more common communication protocol that, say, a computer or a Raspberry Pi can use, such as Bluetooth or USB. We use Bluetooth in our case. From this OBD2 port, we can read values like RPM, throttle position, speed, airflow. There's plenty more like fuel pressure, fuel levels, and other things like that.
The supercharger was the most important component that we had to decide, as it dictates a lot of the other features that the next components will need. Per the problem statement, it needed to produce at least 5 psi and be compatible with as many engines as possible. An issue with superchargers is that if the motor that you're putting it on is too small, you'll have oscillations, and if the motor is too big, it won't be able to produce enough airflow to actually produce useful boost. Another design choice was that it would be able to produce that at lower speeds so that we'd have more freedom in choosing an electric motor to power it with. This graph here shows the Vortec SI trim supercharger that we ended up purchasing. It is capable of producing 5 pounds of boost for a 200 horsepower motor all the way up to 700 horsepower, so it fit the design well of being widely applicable to most modern cars. There's some quick and dirty math you can do to estimate how fast you'll need to spin it, which is these somewhat horizontal lines curving down. And this graph shows us that we need to spin at 27,000-ish RPMs to produce 5 pounds of boost. Since we chose the supercharger, we knew what max RPM we had to hit. We decided with a belt attachment system, so we would be able to choose a pulley ratio. So in order to increase torque, we wanted to step down the motor pulley. So we needed something a little bit faster. We went with the Castle 2028 motor. It is a 3-phased brushless AC motor. It's capable of 45,000 RPMs, which is well within our limits. It has 10 horsepower itself, so it has enough torque to push the motor and gives us a little wiggle room. We decided to go with one with a low pole count because the poles will directly relate to the electrical frequency we need to drive it, and the higher the electrical frequency, the more noise we're inducing in the system. So this allowed us to keep the motor controller next to all our other electronics and still be able to read data out of them. RC hobby-based motors, so there's a lot of documentation on it. A lot of other people are using it for similar high-powered environments. It's waterproof, vibration resistant, so it's perfectly applicable to the environment that we'll be running it in. The next component was the electronic speed controller system, or the ESC. It's used to control the AC motor by converting a pulse width modulation input to a varying frequency. We went with the Hobbywing Easy Run Max 4 ESC as it's rated for 300 amps continuous, which suits the motor perfectly. We're not quite pushing it to that level, so there is a little bit of safety margin there. It's capable of 50 volts as well, which also matches the motor and will influence our battery choice next. It also comes with an over-the-air module, which is accessed via Bluetooth, and it logs data for us, such as engine temperature, speed controller temperature, max currents, impeller speeds, so that we can analyze the data and make sure everything's working as we expect. Lastly, we picked the batteries to match the ESC and motor. They needed to equal 50.4 volts at full charge, so we went with two 6S LiPos for a total of 12S. That's 12 in series, which gave us a 50.4 volt overall rating. They had to be rated at 300 amps or greater discharge rate, which these batteries well exceed at 1400 amps max. The small size was a benefit as well to keep the overall package small.
For our pressure sensor, we went with Honeywell's ABP2 series pressure sensor that could read from 0 to 15 psi, and it uses 3.3 volt I2C communication, so it could be plugged directly into the Raspberry Pi without the need of a level shifter or an ADC. We also designed custom housing to protect the pressure sensor against any hazards that may encounter in the engine bay. So during the full throttle test, we have reached a max motor speed of around 37,500 RPMs, which using the gear ratio, it would be around 29,000 RPMs at the impeller. We used the compressor map to get a rough estimate that should be around 6.35 psi. However, our pressure sensor measured that to be 5.55 psi. During the full throttle run, we were pulling a max phase current of 120 amps, and our batteries experienced 18.5 volt drop. We have successfully integrated OBD2 port into our system, so we now are mapping the throttle response to a PWM signal, which then varies the motor speed and also varies the pressure. We have started to implement PID control into our system, but that was not necessarily for the system to function. Due to the time limit, we were unable to find the right PID values and we were unable to reduce oscillations.